let's talk about NVDC charger design considerations. First requirement is energy star. Energy star means total power draw from the wall when the computing device or mobile device is in a standby state. So here is a diagram about how we define this total power from the wall. So assume this is the input to the mobile device, and the adapter side from wall to this point to the mobile device is typically considered about 50% efficiency. So as the spec says, in standby mode, AC input power from the wall cannot exceed 500 milliwatts. That means the available power coming to the input of the mobile device or the notebook, ultrabook, it's only 250 milliwatts. And from this 250 milliwatts, you have to also, besides the power that's going to the system, you also have to consume power to support the buck converter and support the buck converter switching operation and quiescent current. So typically in today's existing design that's using a hybrid or a traditional architecture, the system power during standby mode is about 180 to 200 milliwatts. So here we listed it's up to 200 milliwatts. That means the charger power consumed from the quiescent current and also from MOSFET switching should be less than 50 milliwatts. Or in other words, the charger's light load efficiency target has to be more than 80% at 20 milliwatt output. And if you don't have special consideration to achieve that, typically the light load efficiency is about only 50 to 60%, which cannot meet this requirement, which means the design has to change on the standby power configuration to lower the total system load, and that's quite some work for the system designers. So we have a goal of 50 milliwatts that we are allowed to consume. How do we minimize the charger power consumption? First, we have to minimize the IC quiescent current. As of today, in the NVDC charger 715, the quiescent current is equals to the quiescent current times the input voltage. And now in 715, it's about 500 microamps. And the gate drive loss, so that means we have to choose a low QG MOSFET because the input is fixed and also because the switching frequency is likely fixed. To minimize this portion of the loss, we have to choose a low QG device. TI's Cyclone FET is the lowest QG device in the market that with a very small RDS(on). So that will help us achieve our goal. And MOSFET switching loss. Traditionally, we are using the PWM control scheme. That means every cycle, the converter is switching. But with given such a light load, it's not necessarily we have to switch in every cycle. So we introduced this PFM mode. That means we regulate the system voltage. So only the system voltage start to drop, then we start to switch. And once the system voltage is going above the regulation threshold, we stop switching. So in that case, we reduce the number of cycles that we have to switch, and then we can minimize the switching loss. Given all the three approaches we are doing, now the 715 charger, we can achieve 82.6% at 2S, 8.4 volts, while a competitor is only 50%, below 50%. At 3 cell, 12.6 volts, we can achieve 86.1% efficiency, while the competitor is only 65%. So here, if you look at the curve, the top two, the purple and red ones, are from our solution, and the blue ones and this brownish ones are the competitor solution. So we can see a significant, much much higher light load efficiency for our TI solution. So using the TI solution, the change to a system to adopt the NVDC charger for standby mode is minimal. Okay, now let's talk about the second thing is how do we deal with various adapters. We talk about the traditional adapters. They are bulky, but they have very strong overcurrent capabilities. But the new ones, the new traveler adapters, they're getting smaller. So even given the same rating, the overcurrent capability might not be that strong. So here is a diagram. We kind of take a few 65-watt adapter and compare their overcurrent delay time. So the x-axis is the OCP current limit, and the y-axis is how long they allow this amount of OCP current limit to last. So here you can see the traditional ones, typically they can allow for 50 to 200 millisecond duration for about 120% to even 180% of OCP, overcurrent capability. But the new ones, or the traveler ones, that's getting smaller, so the typical OCP delay time has been significantly reduced to 5 milliseconds or even close to 1 millisecond. And also the capability is kind of reduced only to like 160%. So given that, what we want to, for the NVDC charger, the requirement is we cannot have such a slow response, so the input will be overloaded. So here is a waveform from an existing competitor solution. Here you can see as the system load comes in, it takes the charger about 1.6 milliseconds to start the input current regulation and reduce the input current. And also not only the time, but the peak power, the peak current drawn from the adapter is 60% above its rating. So that means the overshoot is about 160%. And if you compare to the previous traveler adapter, some of the traveler adapters cannot live with such a long and high overshoot, and it may crash. Now let's look at our solution on the 715. First let's check out the overshoot. Here the overshoot is only 1 amp. And also the duration of the overshoot here only lasts for 160 microsecond. That means within 160 microsecond, the DPM regulation will limit the input current. So you don't have to worry about any chance to overload the adapter or getting close to the adapter overcurrent rating limit. So this we can see a significant reduction on the overloading time and the overshoot amplitude. Meanwhile, we still have some traditional adapters that the user does want to take advantage of its long overcurrent duration. So here, the 715 device offers an option in its register to allow you to disable the DPM. Because if the overcurrent duration is like 50 milliseconds, you do have enough time to use the software like SMBus to enable the DPM again once maybe at about 30-40 millisecond overload. You can come back and enable the DPM because our DPM response is so fast, so that you can take the advantage of a traditional adapter's high current capability. Third thing we want to talk about in NVDC charger design is the system capacitor selection. Here we want to consider a total capacitor value based on the converter stability and also the system voltage transient response. We want to get a reasonable cost number of capacitors with the minimum voltage drop to avoid the system from turning off. So the converter stability, the system cap are required to achieve the loop stability. So typically the 715 output capacitor ranges from 50 microfarad to about 370 microfarad. And the more output capacitance, of course, will help achieve a better output transient response with a minimum system voltage drop or spike. But of course, you spend more money to it. So how do you know the cap is good enough for your system? We need to do some tests. First, let's review the system voltage regulation, how we regulate the system. So when battery is fully depleted and while you're charging the battery, the system is regulated at the minimum system voltage, which is controlled by one of the registers in the 715 charger IC. So typically we do a 3 volt per cell minimum system voltage setting. That's our default. So for one cell it's 3.5 volts, and for 2 cell it is about 6 volts. 2 cell and above, 2 cell, 3 cell, 4 cell, it's all 3 volt per cell. But for one cell, because typical system voltage turn off is about 3.4, so we set the system in to be 3.5. And secondly, we look at the maximum system voltage when charge is disabled. So for us, what we're doing is when the system is not charging the battery, the default system voltage will become 4.5 volt per cell. That means if you are 2 cell, you are doing 9 volt system regulation. If you're 3 cell, you are doing 13.5 volt system regulation. This will help to avoid any instant discharging of the battery if the battery is fully charged. And you have adapter, you just want to fully use the adapter power, not the battery power. So here is some examples how we evaluate if the system cap is enough for your operation. So here, this first example, we have a total system cap of 184 microfarad. And the condition is there's a depleted 2 cell battery, so system is regulated at 6.14 volts. So we apply 240 milliamp to 4.64 amp current step on the load, and the slew is about 1.5 amp per microsecond. Here we do observe the drop is about 312 millivolts. And typically for a 2S operation system, the minimum system voltage is about 5.7 volts. So even with the 312 millivolts, the system voltage drops down to 5.83. We still have about 100 millivolts margin here. So it looks like the 184 microfarad is enough for this kind of low transient. The next example is a different design that we're testing with either 0 amp to 3 amp low transient or 1 amp to 6 amp low transient. Similarly, the battery is depleted and the system is regulated at about 6.14 volts. So now the total system cap is about 300 microfarad, and we do see the system drop is about 312 millivolts for 0 to 3 amps, and only 208 millivolts once the load change from 1 amp to 6 amps. So this tells us this 300 microfarad is enough to support this design operation. This is the fourth thing we talk about is what are we going to do with battery removal. Since in the NVDC charger, there will be lots of the time both the battery and adapter are providing power at the same time to the system. What if but the user never be aware of batteries being discharged to in a supplement mode. So they can at any time they can remove the battery or change the battery if they think based on their needs. So remove the battery really means you lose part of your power source. So we need to think about when battery is removed, how do we doing the best to support system running and inform the CPU as soon as possible to take actions, because I don't think user is expected to see some blue screens once their battery is removed. They just want the PCs to keep operation because the adapter is always connected. So here, what we do is when the battery is removed, we're gonna immediately disable the input current regulation. So this allows the system to draw as much power as it needed from the adapter. Of course, if the adapter doesn't have a very long OCP delay time, it will crash. But this is anyway unavoidable. But what if the adapter does be able to provide like 1 millisecond, 2 milliseconds of additional power? Then this gives enough time for the system to reduce the CPU frequency below the adapter rating, power rating, so the CPU slows down and the adapter itself is enough to provide the whole system power without a battery. So 715 does have a cell pin that will indicate if battery is removed. If once the cell pin is put low, the IDPM is disabled, and here you can see the input current rises to, instead of the original setting of 2 amps, it can go up to 2.5 amps, which is where the system demand is, so that the system keeps running without crashing. Precharge. Typically, if we are in a battery pack, there will be a pair of charging and discharging MOSFET Q2 and Q3 that's connected between the battery cell and the charger. The typical waveforms that you have a much lower precharge current once the battery is below typical, let's say, 3 volt per cell. So that means when we are charging this type of depleted batteries, we have this LDO mode that you regulate your system at VSys min, which is 6 volt for 2 cell and 9 volt for 3 cell. So, and the charging current is regulated, once the charging current is regulated across the sense resistor and to modulate the BAT-FET RDS on, so that your system is regulated as a high enough voltage to keep the system running while you do apply appropriate current to charge your depleted battery. And we do have 384 milliamp clamp current during the pre-charge mode. So we put the battery fed Q3 like a safe operating power condition. So you just need to estimate the power of the battery fed, which is the system voltage minus the battery cell voltage times the charge current. So when you choose the Q3 size, you need to even take the LDO mode into consideration to choose the appropriate rating Q3 for all your operation. But there are some configurations of battery where they do it themselves. The battery pack itself has a pre-charge control circuit. One example is they may have a resistor just to limit the total current going to the battery when it's depleted. So in that case, we can disable the LDO mode. We do have an option to disable the LDO mode. So the system is regulated at the battery charging voltage, and the pre-charge current is set by this resistor. You can just have a rough idea. This pre-charge current is VSys, system voltage minus the battery voltage divided by the R. We define the pre-charge current. So we do have different solutions for the user to choose for different pre-charge requirements for different pack configurations. So we keep talking about while we talk about the design considerations, we do mention keep talking about our solution BQ24715 charger, showing the advantage and how it will be flexible for different system design requirements. Here is a summary of the 715 device, which is already released, and a catalog device in the market. So you're welcome to check it out from the TI website. And this is a main advantage that we have for example, it is a low BOM cost. It all uses NMOS, and it has integrated loop compensation. It has a low quiescent current and high light load efficiency. The quiescent current here listed is maximum value, and typically it's 500 microamps. A fast transient and a small size solution. It has an 800 kilohertz frequency operation, which allows you to choose a smaller size inductor, and it has a 3.5 by 3.5 small footprint package, 20 pin QFN. So here is just a brief summary of this presentation. So as the portable device is requiring for thin, elegant form factors, NVDC charger is adopted more and more in the portable design, like Ultrabook, tablet. They are considering NVDC structure, and TI has developed NVDC charger to meet the market needs. We have lots of considerations from the cost side, from the compatibility from our previous solution like the hybrid and traditional, so can minimize the customer R&D effort. And also we still carry the same kind of safety requirement like smoke-free charger protection to meet the customer safety requirements. And we're glad to share with you about the NVDC system design, some considerations and trade-offs. Hope it will help you to have a better design experience with the NVDC configuration. So in the end, I would like to mention this battery charger search tool that's available from a TI website, from our battery charger webpage, and will help you to pick the right charger that you are interested in.